Another incredibly, surprisingly difficult problem is the Collatz conjecture.
Oh, yes.
Simple to state, beautiful to visualize
Yes.
in its simplicity, and yet extremely difficult to solve. And yet you have been able to make progress. Paul Erdős said about the Collatz conjecture that mathematics may not be ready for such problems.
Right.
Others have stated that it is an extraordinarily difficult problem, completely out of reach. This is in 2010, out of reach of present-day mathematics, and yet you have made some progress. Why is it so difficult to make? Can you actually even explain what it is? It's easy to...
So it's a problem that you can explain. It helps with some visual aids, but yeah. So you take any natural number, like say 13, and you apply the following procedure to it. So if it's even, you divide it by 2. And if it's odd, you multiply it by 3 and add 1. So even numbers get smaller, odd numbers get bigger. So 13 would become 40, because 13 times 3 is 39, add 1, you get 40. So it's a simple process. For odd numbers and even numbers, they're both very easy operations. And then you put them together, it's still reasonably simple. But then you ask what happens when you iterate it. You take the output that you just got and feed it back in. So 13 becomes 40. 40 is now even. Divide by 2 is 20. 20 is still even. Divide by 2, 10. 5. And then 5 times 3 plus 1 is 16. And then 8, 4, 2, 1. So, and then from 1, it goes 1, 4, 2, 1, 4, 2, 1. It cycles forever. So this sequence I just described, 13, 40, 20, 10, and so forth, these are also called hailstone sequences, because there's an oversimplified model of hailstone formation, which is not actually quite correct, but it's so somehow taught to high school students as a first approximation, is that like a little nugget of ice gets an ice crystal forms in a cloud, and it goes up and down because of the wind, and sometimes when it's cold, it acquires a bit more mass, and maybe it melts a little bit, and this process of going up and down creates this sort of partially melted ice, which eventually creates this hailstone, and eventually it falls down to the earth. So the conjecture is that no matter how high you start up, like you take a number which is in the millions or billions, you have this process that goes up if you're odd and down if you're even. It eventually goes down to earth all the time.
No matter where you start with this very simple algorithm, you end up at 1.
Right.
And you might climb for a while.
Right. Yeah. So it's
come down.
Yeah. If you plot it, these sequences, they look like Brownian motion. They look like the stock market. They just go up and down in a seemingly random pattern. And in fact, usually that's what happens. That if you plug in a random number, you can actually prove, at least initially, that it would look like random walk. And that's actually a random walk with a downward drift. It's like if you're always gambling on a roulette at the casino with odds slightly weighted against you. So sometimes you win, sometimes you lose, but in the long run, you lose a bit more than you win. And so normally your wallet will go to 0 if you just keep playing over and over again.
So statistically, it makes sense.
Yes. Yeah. So the result that I proved, roughly speaking, asserts that statistically, like 99% of all inputs would drift down to maybe not all the way to 1, but to be much, much smaller than what you started. So it's like if I told you that if you go to a casino, most of the time you end up, if you keep playing for long enough, you end up with a smaller amount in your wallet than when you started. That's kind of like the result that I proved.
So why is that result, like, can you continue down that thread to prove the full conjecture?
Well, the problem is that I used arguments from probability theory, and there's always this exceptional event. So so in probability we have this law of large numbers, which tells you things like if you play a casino with a game at a casino with a losing expectation, over time you are guaranteed, well, almost surely, with probability as close to 100% as you wish, you're guaranteed to lose money. But there's always this exceptional outlier. Like, it is mathematically possible that even when the game is the odds are not in your favor, you could just keep winning slightly more often than you lose. Very much like how in Navier-Stokes it could be, most of the time your waves can disperse. There could be just one outlier choice of initial conditions that would lead you to blow up, and there could be one outlier choice of a special number that you stick in that shoots off to infinity, while all other numbers crash to Earth, crash to 1.
Yeah.
In fact, there's some mathematicians who've Alex Kantorovich, for instance, who've proposed that that actually these Collatz iterations are like these cellular automata. Actually, if you look at what they happen in binary, they do actually look a little bit like these game of life type patterns. And in an analogy to how the game of life can create these massive like self-replicating objects and so forth, possibly you could create some sort of heavier than air flying machine, a number which is actually encoding this machine, which is just whose job it is to encode, is to create a version of itself which is larger.
Heavier than air machine encoded in a number that flies forever.
Yeah. So Conway, in fact, worked on this problem as well.
Oh, wow.
So Conway, so similar, in fact, that was one of my inspirations for the Navier-Stokes project. Conway studied generalizations of the Collatz problem, where instead of multiplying by 3 and adding 1 or dividing by 2, you have more complicated branching rules. But instead of having 2 cases, maybe you have 17 cases and you go up and down. And he showed that once your iteration gets complicated enough, you can actually encode Turing machines and you can actually make these problems undecidable and do things like this. In fact, he invented a programming language for these kind of fractional linear transformations. He called it FactTran as a play on Fortran. And he showed that you can program it was Turing complete. You could make a program that if your number you inserted in was encoded as a prime, it would sync to 0. It would go down, otherwise it would go up, and things like that. So the general class of problems is really as complicated as all the mathematics.
Some of the mystery of the cellular automata that we talked about, having a mathematical framework to say anything about cellular automata, maybe the same kind of framework is required.
Yeah.
The Collatz conjecture.
Yeah, if you want to do it not statistically, but you really want 100% of all inputs to fall to Earth. Yeah, so what might be feasible is statistically 99%, go to 1, but like everything, that looks hard.
What would you say is, out of these within reach famous problems, is the hardest problem we have today? Is the Riemann hypothesis?
Riemann is up there. P equals NP is a good one because that's a meta problem. Like if you solve that in the positive sense that you can find a P equals NP algorithm, then potentially this solves a lot of other problems as well.